This ICFD++ example tutorial demonstrates the setup procedure for a case of low-speed liquid flow through a three-dimensional multiple pipe junction using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. The tutorial consists of liquid flow through two inlet pipes, one of which causes the flow to expand before making a 90-degree turn into the T-junction. Two different solution algorithms are available for the solution of incompressible flows. These two algorithms are referred to as the preconditioning algorithm and the fully coupled pressure-based algorithm. The use of both algorithms will be illustrated in this example tutorial. In addition, the tutorial will also demonstrate the use of a passive scaler, also known as a color tracer, to mark one of the incoming streams so as to visualize the mixing of the streams within the T-junction. Before starting with the example tutorial, I will briefly cover the new features and components of the ICFD++ AUI for first-time users. For a more in-depth understanding of the ICMP AUI features common across all Metacomp software, please click on the ICMP AUI demo link, which is popping up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. The ICFD++ interface is composed of 5 main components: the menu bar, the toolbar, the canvas, the notebook panel, and the action panel. The first component, called the menu bar, is located at the top of the screen where the mouse is now moving. The menu bar is a common feature across all ICMP components and provides a traditional way of navigating to many of the tools that support CFD++. The second component, called the toolbar, provides shortcuts to the commonly used functions and visualization controls. I'm sweeping the mouse across the toolbar to highlight its location on the screen. The third component, called the canvas, is where the geometry, mesh, or solution is displayed. This component typically occupies the greatest portion of the screen and is located where the mouse is now moving. The mouse is used to control the view of the geometry or mesh within the canvas. You can rotate the three-dimensional view of the geometry by moving the cursor to the canvas and then holding down the left mouse button while simultaneously moving the mouse. You can see that the 3D view changes as I move the mouse about the screen. You can also perform a two-dimensional rotation about the screen axis by simultaneously holding down the right mouse button and moving the mouse left or right. Moving the mouse left will result in a counterclockwise rotation, whereas moving the mouse to the right results in a clockwise rotation. You can zoom the view by also holding down the right mouse button, but by moving the mouse up and down. Moving the mouse up zooms in on the geometry, and moving the mouse down zooms out. Finally, the geometry can be translated or panned across the screen by holding down the middle mouse button and moving the mouse in the direction you wish to move the geometry, as you see on the screen. The fourth component of the AUI interface, called the notebook panel, shows tabs for each ICMP component that is active for the present simulation and one or more information trees. The present screen shows only one notebook for CFD++ and contains a setup wizard, a groups and boundary families information tree, and a boundary conditions information tree. The fifth component is called the action panel, which presents the user with relevant choices that correspond to the active item of the setup wizard action tree and to choices selected in previous and current items of the setup wizard action tree. All of the panels are dockable and resizable to suit your preferences. At this point, I will close the current window so that I can begin the setup of the tutorial example. Here I have the default window, which is obtained when opening the AUI. For this tutorial, I'm using a Linux operating system, and so I launched the AUI by first navigating to my case directory and then by executing the command mcfd AUI. Since I executed the command in the working directory, The directory shows up by default in the select working directory item, and so I can just select the default by clicking OK. The next item in the setup wizard asks if we want to load the grid info and analyze the grid information. This is the first time we've loaded the mesh, so we do want to do that. So we'll leave the default yes for both items and click OK to proceed. When we do that, the grid information window pops up, presenting us with information about the mesh that was loaded into this case. Here we have about 218,000 hexahedral elements, and it also identified 4 boundary families, which is correct for this tutorial, so we'll click OK to proceed. The next window, or the next action panel, is for cell types and volumes. This should be auto-populated based upon what was detected, and so we'll click OK to proceed. We're brought to the general problem definition action panel. We'll leave all the defaults here at general fluids problems. Click OK to proceed. The CFD problem definition panel is where we select the properties of the problem. In this case, we're going to choose a liquid as our fluid type. We're going to leave it as a single species. The fluid is incompressible for this model, so we're going to leave no on the question of is the liquid compressible. We're going to leave yes for viscous. It is turbulent. We are going to say no for energy transport. We're not going to solve energy transport for this tutorial case, and we're going to leave the simulation type as steady state and click OK to proceed. We're not going to apply any additional specifications. We're going to leave all the defaults as no. Click OK. Under the equation properties, this is where we can select our solution methodology. For right now, the first pass through, we're going to leave it at preconditioning. We're going to come back to this step later on though and choose the pressure-based solution methodology. So again, for this first pass, we're going to leave it as preconditioning. We're going to leave the turbulence model at the default 2 equation realizable K epsilon, and we're going to choose yes to define a passive scalar. We're going to leave the default value of 1 and click OK to proceed. We're not going to add any physics source terms. Leave the default no. Click OK to proceed. For units, we're going to solve the problem in SI units, so leave that the default, press OK to proceed. Under fluid properties, primary phase, I'm going to select the incompressible fluid properties 1 and click the icon with a sheet of paper and a pencil here to edit, and verify that the chosen fluid, which defaults to water, is our selection. Here you could select from our large library of other fluid types, but for this tutorial we're going to keep the default of water and continue. The bulk temperature can be changed to 273 Kelvin. And we can click OK and just click OK for the remaining windows to bring us back to the main window. If you didn't edit the incompressible fluid properties, be sure to update the bulk temperature in this panel. And we're also going to add base pressure. We're going to just set it to atmospheric, so 101,325 for base pressure. We're going to leave the laminar Schmidt number at the default 0.7, and we are not going to turn on buoyancy effects, so we can at this point click OK to proceed. The next item in the setup wizard action tree is the definition of the initial conditions. Here we're going to leave it as the entire domain, which is the default value, and we're going to create a new information set for the initial conditions. So we click the green plus. We're going to select the new information set that was created. We're going to set the static pressure to 0.0, keeping in mind that this static pressure is relative to the base pressure, which we set in a previous panel to atmospheric. So by setting it to 0, we're actually setting the initial conditions to the atmospheric pressure. There is not a uniform direction of flow for this problem, so the initial velocity components will be left at 0. The turbulence quantities will be left at their default. We're going to come back later in the setup and use the turbulence initialization tool to set those properties for all of the information sets that we define. And the passive scalar, we're going to leave the initial condition value of 0.0 and select OK to continue. The next action panel is for the boundary conditions. So we're going to stop here for just a moment and come back over to the groups and boundary families tree and talk a little bit about what we see here. When the problem was loaded, it identified 4 boundary families. And these boundary families were loaded in, and there are 3 icons next to each one. There's a red X. The red X indicates that these boundary families have not yet been associated with a boundary condition. And that's what we're going to do here in this step. The next icon changes the display of the mesh. So right now we have a wireframe view, and the third turns on shading. So we can change the view of our wall here by toggling these 2 icons to have the selection however we prefer, with some combination of wireframe and shading. In this case, I'm going to just leave everything in their default view. One other feature, though, to show is sometimes we need to find specific boundary conditions in our model, and we can click on these boundary families to identify, and they'll be highlighted in white to help us identify where in the model each of these boundary families is located. All right, so let's define our boundary conditions. We're going to start with inlet 1. If I click here, we can see inlet 1 is highlighted on this leftmost lower inlet face. This is an inlet boundary condition, so I'm going to click to select the boundary family, then I'm going to click and hold and drag it over and define a new open boundary condition which this boundary family will be associated to or associated with. Inlet 1 will be designated as an inflow-outflow boundary condition subgroup. We're going to leave it as a primitive variable, and under this there will be one info set already defined. However, this information set corresponds with the initial conditions that we previously defined, and so we don't want to use this as the definition of our boundary condition. So we're going to select on the temperature-based primitive variables tree, and we're going to add a new item to that tree, or a new information set. We're going to select the new information set we created. We're going to set the pressure to 0. We're going to set a y velocity of 1.0 meter per second. We're going to leave the turbulence quantities for later. And we're going to set the passive scalar value to 1.0. So this leftmost boundary, this is where we'll be applying the passive scalar, and we'll be observing how it mixes with the remainder of the flow. So we'll click OK to accept those settings. If we notice now up on the boundary families tree, there's now a green check next to inlet 1, which indicates that this boundary family has been associated with a boundary condition. There's also a new entry in the boundary conditions tree that corresponds to the new boundary condition that we have just created. Now for inlet 2, we're going to highlight inlet 2, and we're going to left click and drag, bring it over to an open boundary condition. We're going to define a new open boundary condition for inlet 2. Okay, inlet 2 is also going to be an inflow-outflow boundary condition. Again, the information sets, the first one corresponds to the initial conditions, the second one corresponds to the properties for inlet 1, so we need to define a new information set for inlet 2. Click the green plus. When that appears, we're going to select the new information set, set the static pressure to 0. The y velocity for this boundary will be 2.2 meters per second. We'll leave turbulence quantities for the turbulence initialization tool, And the passive scalar we will leave at 0 for this boundary. Click OK to proceed. Now we can see inlet 2 now has a green check identifying that this boundary family has been associated with a boundary condition. Now to tell the differences between the boundary conditions that have been defined, we can leave the mouse over the boundary condition and it brings open a window showing the values that have been associated with that boundary condition, so we can identify which boundaries have which properties. Now we need to define the outlet boundary condition. The outlet, again, if we want to see where it's located, we can click to highlight the outlet boundary family, and the faces associated with that boundary family will be highlighted in white. Now sometimes when we have a very long list of boundary families, this list is quite short, but with a longer list you might see that sometimes it can be difficult to determine which boundary families are remaining to be selected from the menu here in the action panel. So what we can do is we can actually select items from the groups and boundary families tree, and they can be brought over to the boundary conditions to define, just as we brought them over from this leftmost boundary families tree. Now the outlet boundary is going to be outflow only for the subgroup. We are going to have a pressure with a back pressure imposition. We need to define a new information set, so click on the green plus, select the new information set, and set the back pressure to 0.0, and then select OK. The remaining boundary family is the wall boundary family, so we left click on wall, and then left click and drag over to the wall boundary condition type. Here we're going to leave the wall type as viscous. We're going to turn the wall integration type to wall function, leave all other values in their default, and click OK to continue. At this point, all of our boundary families now have a green check next to them, so we can proceed to the next item in the Setup Wizard action tree by clicking OK. This brings us to the turbulence control entry for the turbulent wall functions. At this point, the only thing we're going to change is the turbulent Schmidt number. We're going to set to 1.0 and then click OK, which brings us to the turbulence initialization tool. Now here we have the three information sets that we need to define the turbulence properties within. The first is for the initial conditions, and there is no velocity associated with that, and the velocity is necessary for calculating k and epsilon. So we're going to skip over that one, and we're going to go to the second information set, primitive variables 2. And up here we have a hint in blue text that says to left click on an information set to select it. So I left clicked on the primitive variables 2, and then we right click to initialize the turbulence quantity. So I'm going to right click, and it brings open the turbulence calculator. In this case, we're going to set the free stream turbulence level to 0.05 and leave the dimensional turbulence length scale to 0.01, and the free stream velocity is auto-detected from the information set. So at this point we can just click compute to compute k and epsilon quantities, click OK to acknowledge, and then OK to close, and we can see that k and epsilon have been updated for the primitive variables 2 information set. We can repeat this process for primitive variables 3. Simply left click to select, right click to bring up the turbulence calculator. The previous quantities are already entered, except that the free stream velocity has been updated to use the value for this information set. So all we have to do is click compute, acknowledge with the OK, and click OK. Now we still need to define the turbulence quantities for primitive variables 1. Now again, we don't have a velocity component here, but what we're going to do is use our Copy Information Sets tool. And we're going to copy the values by selecting primitive variables 2 as our source, and our destination would be the primitive variables 1 that we need to define yet. Now, if you notice, if I put the mouse over each of these information sets, the values associated with that information set are shown. And this helps you to see that primitive variables 2 and primitive variables 3 have already been defined for k and epsilon, and it's primitive variables 1 that we need to select. So that can help you confirm which source and destination you want to use. So once I have selected my source and destination, I simply click the Apply and OK. And now as I click through the menu of all of these, we can see that indeed the k and epsilon have been set for each of these information sets. So at this point we can click OK in the action panel to proceed to the next item, which is the Help Set Numerics panel. In this case, we are going to choose Yes to help us set the numerics. The only thing we need to enter here is an approximate system velocity for the preconditioning. And here we're going to put in 2.0 meters per second. Click OK. We're going to accept all of the defaults for the Riemann solvers. Again, we're going to accept the defaults for the simulation strategy. All of these have been set up with the Help Set Numerics wizard. So click OK. Same thing with the time integration. Everything has been set up for us, and so we can just select the defaults by clicking OK. Spatial discretization tab. It auto detects that this is a 3D problem. So again, we can select the defaults by clicking OK. And this brings us to the neutral plot file options action panel. And here we can select the variables that will be output in the neutral plot files. In this case, for turbulence, we're going to activate the turbulent eddy viscosity in the output. And we're going to scroll down to the right-hand side and color, user-defined variables. And we're going to activate color 1 since we do have a passive scalar or a color quantity that we are going to be calculating. So we need to output that in our neutral plot file. So at this point we can click OK to continue. It just will prompt us with whether or not we want to write those control files. We do, so we'll click OK. And then we're brought to the probe and output files action panel. And this is where you could set properties for writing out your solution restart, neutral plot file, or third-party visualizers. For this example, we're just going to accept the default values. Click OK to proceed past this panel. And the final step is to save the input file and to run CFD++. Here we're going to start running this case. This case does take a while to run on the laptop, so we're not going to run it to completion, but we're going to start it here by clicking OK. So first it saves the input file, and then we'll bring up a display showing the log file as the case starts to run. And at this point, we'll let it run for one step here, and then just click the clean stop. In that case, we'll stop running. And that completes the setup for the preconditioning based approach. For visualizing the results, you can see the results section of this example problem. But for right now, we're going to take a step back and we're going to look at how we would change the setup to use the pressure-based solution method. Now we could start from scratch, start over with a new case with only the mesh files, and most of the inputs will be identical to what we have done here. So in this case, what I'm going to do is actually show a feature of the setup wizard where we can go back, change inputs in earlier items of the setup wizard, and we'll show you what happens here. So we're going to go back to the equation properties entry in the setup wizard where we chose the preconditioning solution methodology. And we're simply going to change that from preconditioning to pressure-based. And when we do that, a red X now appears before the equation properties, meaning that something has changed in the panel and that we need to acknowledge that before we can proceed. So we'll just click OK. Again, we're going to leave the same turbulence models we had used before, and again, leaving the definition of the passive scalar. So simply change it to pressure-based and click OK. And when you do this, it skips all the way down to the Help Set Numerics tab, which has a red X. And if we scan down, we see many other red X's in the remaining items that we have already set up previously. But here, since we've changed the numerical scheme, we need to, again, go through these items, altering our selection based upon the change now from the preconditioning approach to the pressure-based approach. And so CFD++ auto detects which of these entries need to be updated and will display a red X showing you that you need to go back and modify those. So here we are going to use the Help Set Numerics tab as we had done before. We can see the options are slightly different. We no longer have to enter the approximate system velocity for preconditioning, since this is now the pressure-based approach and it uses a different algorithm. So we're going to leave the defaults here, click OK to continue. The Riemann solvers, if we were to look through the advanced controls, we might see some differences, but for this example case, we're going to leave the defaults, click OK. Simulation strategy. For this case, if we were going to actually run it, we're going to increase the number of global time steps, but that would be the only change to the simulation strategy action panel. Under time integration, again, the specific options or the specific questions that need to be answered are different between the pressure-based and the previous preconditioning approach, but we're going to leave all of these as default values and click OK to continue. Spatial discretization is the same. Click OK to continue with the defaults. And the neutral plot file, you will be prompted to make any changes if you so desired, because we did change the numerical scheme, but in this case we don't want to change any variables that we're going to output, so we're just going to click OK to continue and acknowledge the writing of the control files. And then we're brought to save the input file and run CFD++ as before, so we can click OK to continue. So you can see that you can go back to previous steps in the setup wizard, alter numerical settings or alter boundary conditions, and the code will auto-detect what items of the panel need to be reviewed and new selections made. So at this point, we'll stop this run. And again, for the visualization of the results and the post-processing, we can see the results section of this tutorial. Thank you.